Hello, and welcome to Team Eagle Energy's Senior Design Project, Novel Heating System for the Battery of a Lunar Rover. This project is brought to you by the Department of Mechanical and Electrical Engineering at UT Tyler at the Houston Engineering Center. This project couldn't have been done without the contributions of Sambrin Coda, Aviola Ilori, Fernando Loyola, Marcos Martinez, Ihan Ponguira, Abdullah Sishinwari, our sponsors from NASA and TSGC, and our advisor Oz Al-Shalash.
Our goal is to design a novel heating system for a Lunar Rover battery. The battery must survive 100 hours of lunar night while using minimal mass and power requirements. The purpose is to keep the battery between operational temperatures, which are 5 to 20 degrees Celsius. During lunar night, the rover goes into a low power mode, which will turn off the rover thermal management system. Our design will be replacing the radioisotope heater units, which will be used once the rovers go to low power mode. The design should be capable of producing 1 watt of thermal power per kilogram of mass. NASA is planning to continue exploration on the moon after confirming the existence of ice water. The main focus will be located in the lunar South Pole. The ambient temperature during a lunar night goes down to negative 230 degrees Celsius. These harsh conditions necessitate the heating of core components.
The final design adopted basic chemistry principles to produce heat. The rusting of fine iron wool generates heat that is used to warm the battery. It is important to note that iron only rusts in the presence of oxygen in water. The reaction is housed in a pressure-rated sleeve and regulated by a solenoid valve. 6061 aluminum was chosen for the oxygen tank and the reaction chamber because of its resistance to corrosion and its lightweight. Stainless steel was selected for the oxygen tubings for similar purposes. A self-priming diaphragm pump pushes water through a high-braided pressure-rated tubing, and brass, which is resistant to corrosion, was best suited for the spray nozzles.
The system kicks into action when the temperature sensor attached to the battery falls below 5 degrees Celsius. This sensor sends a signal for the solenoid valves to open, releasing the reactants into the reaction chambers. Then, the reaction starts generating heat, which is transferred to the battery through conduction. Once the battery's temperature sensor climbs to 5 degrees Celsius, the solenoid valves shut off. As time progresses, the battery starts cooling down again, starting the cycle once more. The final assembly consists of 3 systems: the oxygen distribution system, the water distribution system, and the failsafe system. As the oxygen enters the chamber, it encounters stripped iron wool and starts the reaction. The circles embedded into the stripped iron wool are temperature sensors for monitoring data. Water is dispensed from the water tank into a DC water pump, which distributes the fluid across all 4 chambers, passing through the water solenoid valves. Once inside the chamber, the water is finally misted into the stripped iron wool. Attached to the inner upper part of the chamber is a humidity sensor for data acquisition purposes. If the temperature is too high inside of the reaction chambers, the solenoids shut off immediately and the reactants left in the chamber are channeled to the failsafe system.
In order to visualize the effects of ambient cooling on the system, as well as the heat generation due to the exothermic reaction, a transient thermal finite element analysis was conducted using ANSYS Workbench. The geometry of the model consists of the battery surrounded by 4 adjacent reaction chambers, sitting atop a layer of MLI and the rover body. The thermal loads applied are intended to simulate the heating system's operation during rover shutdown and lunar night. This is done by applying a constant internal heat generation within the iron wool, as well as a constant temperature of negative 230 degrees Celsius at the bottom surface of the rover body. The animations represent the heating of the system that occurs once the set point temperature of 5 degrees Celsius has been reached. This triggers the reactants to release into the chamber, beginning the reaction. The temperature will continue to fall as the reaction begins generating heat, with the heat generated eventually overtaking the ambient cooling. Eventually, the heat generated will warm the battery back to the set point temperature of 5 degrees Celsius, where the solenoid valves will close, stopping the release of new reactants into the reaction chamber. However, the reaction will continue with the reactants still remaining inside the chamber, heating the battery past the set point, but within its operating range, until these reactants already transported into the reaction chambers are used up. Once this occurs, the battery begins to cool down once again, eventually restarting the cycle. For the final design, 18 moles of reaction are stored within the system, which provides a total of 28.7 millijoules of energy. 3 parameters were used when determining the amount of reactants to pack within the system for 100 hours of use. First, the energy provided by the reactants needed to be enough to offset the ambient cooling effects. This goal is achieved relatively easily with only 5.31 moles of reaction needed to generate this heat. Next, the total weight of the system must not exceed 10% of the weight of the rover, meaning the system must weigh less than 90 kg, reactants and all. Finally, the thermal power to weight ratio offered by the system must exceed 1 watt per kg of mass added in order to justify the system's use over existing heating solutions. 18 moles of reactants provides the best balance of these parameters while meeting all the specifications required as well as maintaining cycle performance. Adding more reactants while keeping the existing infrastructure the same would influence other variables such as rate of reaction and heating overshoot. In order to create a prototype of the reaction chamber, a scaled-down version was designed and assembled. The oxygen is distributed to the system in the same fashion as the final design, however a manual valve was used instead of a solenoid. The same goes for the water distribution system, where water is fed by a DC pump into the chamber where misting nozzles disperse the water evenly on the iron wool.
3 types of sensors are used to capture the data: humidity sensor, pressure sensor, and a temperature sensor. Humidity sensor is used to measure the contents of moisture present inside the reaction chamber prior to the release of oxygen. Pressure sensor is used to monitor the pressure inside the reaction chamber before and during the operation to ensure the safety and integrity of the structure of the reaction chamber. We have used 4 temperature sensors located strategically to record the temperature across the geometry of reaction chamber. They are placed in different areas of the iron wool. As the oxygen is released into reaction chamber, the sensor will record the change in temperature.
To increase the efficiency of system, a reaction sleeve was constructed with the help of a stationary power tool like CNC machine, drill press, disc and belt sander. In order to remove the protective layer from iron wool and pack the iron wool inside the sleeve, a low vacuum packing chamber was prepared. The vacuum chamber is made of clear plastic box with integrated gloves. The vacuum packing chamber is great for keeping air-sensitive material from contact with air or moisture. What we were able to achieve through our project is the design of a novel system that not only weighs less than 10% of rover's weight but also delivers 1.024 watt of thermal power per kilogram of mass added. Additionally, our system is reusable and simple to maintain and repair. That concludes our presentation.
A very special thanks to Dr. Barakat, Dr. Garcia, Mr. Ashalash, Mr. Alvarez Hernandez, and Dr. Tim Urban. Thank you.